Okay, so in this lecture, we're going to cover section 2.5, which is on continuous functions. So far we've introduced the notion of a limit, and this is a very fundamental concept to calculus, and really a fundamental concept to all of mathematics, or lots of different branches of mathematics. And we explored properties of limits and different ways and rules and techniques for computing limits and dealing with limits, and for a broad class of different limits. And now we're going to look at continuous functions, and this is the next most important concept in calculus. We're going to look at continuous functions, then we're going to look at differentiable functions, and then we're going to look at integrable functions. These are all very important classes of functions. Um, it's going to turn out that um, there's like a containment of these functions. We have differentiable functions are contained in continuous functions, and then the continuous functions are contained in integrable functions. But these are proper containments. So for now, though, we're just going to look at continuous functions. So let me share my screen now and pull up the book. All right. So as I said, we're in 2.5 on continuity. We're talking about continuous functions. And this definition here should look somewhat familiar. Familiar. This was we there was a theorem in 2.3, I guess, or 4. Let me just pull it up, actually. Why don't I just pull it up? I think it's 2.3. It was a theorem on polynomials. Yes, right here. It was this direct substitution property, and it said that if you have a polynomial or a rational function, so polynomial or a rational function, and this point A is in the domain of f, then to compute this limit right here, you could just simply, the limit of f of x as x goes to a, you just simply evaluate the polynomial or the rational function at that point. We proved this substitution property for um we proved this substitution property for polynomials, and then from there you can just easily prove it for rational functions. And it turns out that this is the right definition of um, continuity for a function to be continuous. We're used to thinking about continuous functions as being those functions whose graphs can be drawn continuously without lifting the pencil, and that's an intuitive way of thinking about continuous functions. But it turns out that this definition captures that idea, and so polynomials are like the paradigm of a continuous function, so they certainly have this property, which we proved. And it turns out, but there are functions there are continuous functions which are not polynomials. So for example, trig functions are going to turn out to be continuous. Exponential functions, logarithmic functions, these are going to be continuous functions, and some but none of them are rational, or even they're not polynomials or even rational functions. So the set of continuous functions is bigger than the set of polynomials. But this is the essence of continuity right here. So let me go back to the section on continuity. Um, and so this basically says that when you take this, so it's, first of all, this is continuity at a specific number, and it'll turn out you can be continuous on a set of numbers, and to be continuous on a set of numbers means you're continuous at every number in the set. So that's a very easy concept to understand once you know what continuous at a number means. And to be continuous at a number just means that when you look at the function and you take numbers x that are getting closer to a from either the left or the right, and you evaluate this function, you're going to get, in a sense, like this sequence of numbers, maybe like a sequence of numbers when you consider x to the left, and a sequence of numbers when you consider x to the right, or just any way of mixing those two, maybe like considering a sequence that swaps from left to right. And these numbers are going to converge or approach a number, and the number they approach actually is just the value of the function at that point. And as this book notes, there's actually this definition implicitly assumes three things. First of all, the function has to be defined at this point. So this is a pretty strong requirement. There's going to be a lot packed in this definition, the definition of continuity. Um, so it's going to require that f is defined at a, that is, it's in the domain. I mean, you can't even write this down. You can't write f of a if a is not in the domain of f. It wouldn't make sense. So first of all, and then the next thing is that this limit exists. And then finally, the what it says is that not only does this limit exist, but it equals the value of the function. Um, so here's like a graph illustrating the idea. You have this point A that we're going to approach either from the left or the right, and then we have f of a, and it actually is point on the graph. Well, it's like connected to the rest of the graph in a sense. In other words, f of a is not some point way up here where you have this jump. It's connected to the rest of the graph. There's like this smooth transition to the point f of a. And so if you consider points to the left or points to the right, and then you look at the f of those values, you can see they're getting closer and closer to what f of a is. So that's what continuity is. And so you can see, yeah, this does capture that idea of the fact that you can draw your graph without lifting the pencil in principle. And this is an important procedure in math. When you come up with definitions in mathematics, they're almost always based in some sort of intuitive idea, some concrete problem. And you always want to, when you come up with a definition, you want to test the definition against your intuition, or test your definition or your idea against the problem that you're trying to solve. So always compare, always want to compare those two. So now that's what it means to be continuous. Um, let's see, what else does it say? So f is defined at near a. Yeah, so that the limit actually presupposes that you're defined near a, that is, you're defined in an open interval containing a, and you're actually defined there. Now, when you are, and then what does it mean to be discontinuous? It just means not continuous at that point. And there are actually three ways that this can happen, right? Because because this definition implicitly requires or presupposes that there are three ways you can fail to be continuous, or there are three ways you can be discontinuous. So what are those ways? Well, there's three ways, and they just mirror this. They kind of are mirror this in a sense. Well, the first way is that um, f of a is not defined. So if you're not defined at this point, you definitely can't be continuous at it. Another way would be that this limit doesn't exist. I'm going to say does not exist, DNE. And the last would be that maybe this limit exists. So the limit exists, but it doesn't equal f of a. Maybe like you have a jump up here. So like these are approaching. So and then where the red circle is right here, you have actually have a hole or a gap. And so you're approaching this number, but f of a is way up here or something. And so the limit exists, but it doesn't, and f is defined at a, but you don't have this, you have inequality here. So this is going to be three different ways. And these are the only ways really you can fail to be discontinuous. And this is actually going to lead to a classification of discontinuities. We're going to have a threefold classification of discontinuities. And that which will be really helpful. And we'll look at those later. So why do we care about continuity? Well, continuity is something that comes up a lot in nature. A lot of physical phenomena are continuous. So, for example, changing your position is a continuous process. You don't just when you're moving, when you're driving in a car, when you're flying in a plane, traveling on a train or whatever, you don't just teleport to your destination. It's this continuous process. So changing your position is a continuous process, and so is it velocity. Velocity is a continuous process also. You don't just suddenly, you're not like going 50 miles per hour and then suddenly jump to 60. You have to pass through, you know, 51 miles per hour, 52 miles per hour, et cetera, up to 50. And then even more fine grained than that, you have to do 51.5 miles, 51.75 miles, et cetera. You have to continuously pass through these values to go from 50 miles per hour to 60 miles per hour. And that's actually going to be really important when we go to the intermediate value theorem. This idea of having to pass through all these values in a continuous fashion. We can actually um, mathematically prove that. And this is called the intermediate value theorem. Um, Now, as it says, there are discontinuities that do occur in nature. Also, like with electric currents, like when you flip a switch on and off, it's just it's it's a discontinuous process, the flow of electricity. So discontinuities do to occur, and that's what makes, I guess, studying physics interesting. If everything were continuous, physics would kind of be boring in a sense. But a lot of phenomenon is continuous or can be modeled as continuous. So maybe things in nature aren't perfectly continuous, but they can be approximated as continuous. So this is a very important concept, that of continuity. And then bring up another example when I was talking about heating a room. You have like a room and you have a heat source. The increase of temperature is a continuous process. You don't just suddenly go from a certain temperature and jump to another temperature immediately. It's a continuous process. It might happen very fast, but it's still a continuous process. So that's continuity, and then this is discontinuity. It just means not continuous. And then there are three ways you can fail to be continuous, based on the fact that this definition of continuity presupposes three different things. Here's a picture of illustrating that, and here's a picture illustrating some discontinuities. So we have a discontinuity here, here, and here, and all the other points on the curve are continuous because they're joined together in a sense. Um, but these kind of illustrate the different types of, or at least two of the discontinuities you can have. So the first, one of the discontinuities is a jump discontinuity, and that's sort of what we have at three. This would be like your change temperature being, some one temperature and then suddenly jumping up and not even equaling that temperature because you have an open circle there. So that's definitely not something that can happen in nature. And then so that's three is a jump discontinuity, and then one and five are going to be called removable discontinuities. So here, five really illustrates what I was trying to illustrate up here with this dot. So when you take this limit as x approaches five, from the left or from the right, and then you look at the corresponding uh, f of those values, you can see that they're approaching this hole right here. So this will be some number, maybe it's, I don't know, if you trace it over here, I guess it's right there. And then the value, this right here is going to be f of 5. And you can see that they don't equal each other. So intuitively we want to say, yeah, this function is not continuous at 5, but it also matches with the definition. So we have there's like this duality in mathematics of intuition and rigor. We want to use intuition to guide us in formulating ideas, but once we formulate those ideas, they have to be rigorous. And so, but we need these things to be compatible and in sync in a sense. So that's these are discontinuities, but they're called removable because you can redefine the function and in a sense by like filling in the hole. And we'll make that more precise later. All right, so here are some functions where we have some types of discontinuities. So we have A. So first of all, this illustrates the first type of discontinuity you can have where you're just not simply not defined at that point. So uh, this f of 2 is not defined because you have division by 0, so can't be continuous there. Now what about B? So The only problem, so if you look at B, and if you look at a point away from 2, you're going to be this rational function, and these are continuous. Remember, they satisfy the direct substitution property. Remember that, or that theorem that was about the direct substitution property. That basically tells you that these functions are continuous. So away from, so in other words, because because f of x is this rational function away from 2, we can say it's continuous. So f away from 2, that is not equal to 2, from 2 is rational and hence continuous by direct substitution property. I think that's what it was called, direct sub property. All right, so the question is, all right, well, what about at 2? That's really the crux of the map problem, right? Like, is this thing continuous at 2? Well, we have to check it by definition. We have to compute a limit and then evaluate the function at that point. So let's do that. So first of all, we know f of 2 is equal to 1. But now we can compute this limit as you approach 2. So now remember, in limits, x is not going to be equal to 2. It's going to be close to 2, but not equal to 2. So that's why when we evaluate the limit of x, it's going to be equal to the rational function, because we're not considering x equal to 2. So when x is not equal to 2, it's equal to this rational function. And this rational function can be factored as follows, and then you can cancel this term with this term, and then you can just take this limit, and you can do, I don't know, I guess a direct substitution, yeah, because this is a polynomial. So you get 2 plus 1 is 3. So 2 plus 1, so 3 is not equal to 1. So we have that this fails. We don't have equality, so this is not continuous right here. So in other words, the limit exists and f of 2 exists, it's defined, but they don't equal. So that's that, when I was talking about discontinuities up here, that'd be this third point right here. The limits exist and the function is defined at the point, but they don't agree. And then what about this one? I don't care about D. Don't even worry about that one. What about C though? So C, so we have another piecewise function. So again, for this exact same reason over here, the function f away from 0 is a rational function, right? It's 1 over x squared. So when x is not 0, you get 1 over x squared. So this is f is continuous outside of away from 0. Now the question then becomes is, well, what about when it's 0? Do we have continuity at x equals 0? And I guess we just do a calculation here. Well, this limit actually, well, it does exist. I don't know why they're saying it doesn't exist. So first of all, f of 0 is 1. So f of 0 equals 1 exists. But this limit is infinity. I think we have a graph here, right? So yeah, so if this is C, this is the graph of 1 over x squared. What's the graph of f of x? So this part C is the graph. F of x is equal to 1 over x squared when x is not 0, and then 1 when x is 0. So when x is 0, f of x is 1. And then as you get close to 0, but not equal to 0, the function goes off to infinity on either side, positive infinity. So the limit does actually exist. It equals infinity, but that's definitely not equal to 1 right here. So they don't agree. So this is going to be an infinite discontinuity, as it says. So here, this is that threefold. This is that trifold trichotomy. I guess, yeah, not dichotomy, but trichotomy. We have this trichotomy of discontinuity. So we have in parts A and B, we have removable discontinuity. And the reason why is that we can remove the discontinuity, as I said, we can remove the discontinuity by redefining f at that single number 2. So we have we have a and b, and they almost basically these two functions are the same except that x equals 2. But what you can do is you can just redefine the function at us at the single point x equals 2 in both cases, and just define it so that I don't know what point that would be, I guess oh, it'd be 3. So you can redefine it so that f of 2 equals 3. Maybe you want to use a different symbol like f bar because you want to technically distinguish it from the function, the original function. So you have like f bar of 2 is equal to 3, and then you basically just fill in the gap, and then you get rid of that circle right there. So removable discontinuity just means you can redefine the function. Yeah, so right here it says, as I was just saying, if you redefine f to be 3 at x equals 2, then f is equivalent to this function g of x. Yeah, so they're going to call the new function, the function that you redefine, to be g of x. And it's just going to end up being x plus 1. So this, when you redefine the function in a or b by defining it to have a different value than it does at 2, you get this new function g of x, and it ends up just being the line x plus 1, which is what we saw when we did this limit calculation. In part C, we have an infinite discontinuity. This is not, these are mutually exclusive. You can't be a removable discontinuity and an infinite discontinuity. There's no way to redefine this function in part C so that you get continuity at x equals 0. It's impossible. It's just the function. This is actually called, sometimes they call this a singularity. It's too badly behaved near x equals 0 that there's just no possible way to redefine this. And you can kind of have the same thing with this jump discontinuity also. There's no possible way to redefine this. This is the function we didn't look at, but we already saw just jump discontinuity up here at this point 3. All right. Let's see. And so now we naturally get this notion of right and left continuity. So you can talk left and right limits, hand limits. So you can talk about right and left hand continuity. So it's a pretty natural idea here. This is probably not going to come up a whole lot. They use this integer. They use this example 3. I guess I could technically talk about this too. They define it up here. They don't define it, but this is just like this function right here is called the greatest integer function, I think. So basically, like if you plug in a number, let me look at the graph to remember it's how it's defined. So if you plug in 1/2, uh, so if you plug in, oh, sorry, no, let me see. If you plug in, it's like 1.5, you get 1. Okay, so this function, it's like var x, I don't know, is the greatest integer function. And basically how you evaluate is f of x equals the integer. What's the best way to, I'm trying to state this rigorously. So that equals the integer. It equals the smallest integer greater than x. So for example, if you, let's say, for example, if you do the greatest integer function of, say, 3/2, this is, well, this would be 1.5. Oh, this is not right. I think I have it backwards actually. It's the largest integer. I think it should be it's the largest integer smaller than x. Sorry. It's the largest integer smaller than x. So for example, this evaluates to 1. So there are a lot of integers smaller than 1.5, right? There's 1 is smaller than 1.5, 0 is smaller than 1.5, -1 is smaller than 1.5, -2 is smaller than 1.5, etc. But there's one integer that is smaller than it and bigger than all the rest of ones that are smaller than it. So that's 1, because 1 is bigger than 0, 1 is bigger than -1, 1 is bigger than -2, etc. So that's how you evaluate that. And I guess another one would be like pi, greatest integer function of pi would be 3, because pi is like 3.14, blah 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 blah, etc. And so like this the integer just smaller than it would be 3. So that's how you define that. And I guess they're just proving it's continuous from the right, but not is discontinuous from the left. Okay. Yeah, all right. Anyways, I don't care about this example. You can, I mean, if you're interested, you can look at this. All right, so now we talked about continuous at a point, but now we can just talk about continuous on an interval, and it just means that you're continuous at every number in the interval. So pretty straightforward definition. So here's an example. We want to prove that this function is continuous on the interval -1 to 1. Now we have to be careful about the endpoints, okay? So here we do need to talk about continuous from the left to the right, because the function you can't evaluate this function to the left of -1. You can't evaluate it to the right of 1. You'll get a square root of a negative number. So you can't take the limit of this as x approaches -1. You can't take the limit of this as x approaches +1, because that will include numbers that are on the left and the right of each one, and you could get possibly square root of a negative number. So you have to, when you're doing this, when you want to check continuity at the endpoint, say -1, you got to take the right hand limit, so that you're talking about x values that are just a little bit bigger than x. And then for the positive one, when you want to check continuity at +1, you have to do continuity from the left, because you want to take numbers x's that are just a little bit smaller than -1, and that will ensure that this square root here that you're taking the square root of a positive number. But first, let's just talk about the interior of this interval. So strictly between -1 and 1. And this is just a pretty straightforward calculation to show continuity. And the reason why this is straightforward is that because we have all these limit laws available to us. We have all these limit laws. And actually, before I go through I'm sure you're reading these already. Before I go through this, I want to go back to the definition of continuity and spell out in terms of epsilons and definite deltas, because there's a lot jam-packed in this. So this definition right here is equivalent to the following. If we can rephrase this, it's equivalent to the following. We can rephrase this in terms of epsilon deltas, because the limit itself is defined in terms of an epsilon delta. So let's say, let's call this equation right here star. So star holds if and only if, what? Well, let's remember the epsilon delta definition of a limit. For every small number, positive number epsilon, there exists a small number delta such that x minus a being less than delta implies that f of x minus f of a absolute value is less than epsilon. So this is pretty familiar. Before, when we were talking about limits, the limit we said was equal to L, so like this would f of a would be replaced by L. But now we're making a stronger requirement. We're not just saying that f of x just equals some number L, but it actually, or sorry, f of x minus f of a is less than epsilon. We're not saying that that's less than epsilon just for any L, but specifically f of a. So as I said, there's a lot jam-packed in this definition of continuity. But we don't have to resort to this definition in terms of epsilon and deltas, because we have all our limit laws available to us that you prove using the epsilon delta definition. So let's go back to that example, see how that works out. So as you can imagine, if you wanted to prove this using the epsilon delta definition of continuity, that'd be pretty awful. But this is the power of abstraction and proving your theory and drawing the consequences of your theory, is that you can avoid these technical calculations. So to prove continuity, we just need to compute this limit and then show it equals f of a. Well, why is that the case? Well, when we take the limit of this, it's same as taking as the limit of 1 minus square root of x, square root of 1 minus x squared. And this is a sum of functions, so we can distribute the limit over, and we have just this constant that hangs around. And then we take in the limit of a square root. Well, we know that the limit can be brought inside the square root. And finally, what we have is just this polynomial right here. And we can say, polynomials are continuous, or we can just say by the direct substitution law, to evaluate this, we just plug in a. But this right here is just the function evaluated at a. So that's why we get continuity there. And so that gives us continuity on the interval -1 to 1, but we need to check now the endpoints of this the interval. This is the interior of the interval -1 to 1, including -1 and 1. So for continuity at the endpoints, we need to take the limit as x goes to -1 from the right, and we could just evaluate that. Well, we can just see that it's just going to be 1, because we can just use the function itself, and that's the same thing as evaluating the function at -1. And just as it says, going through these exact calculations right here, we can do these left and right hand, or this right hand and this left hand limit. And then this will tell us that it's continuous on the whole interval. All right, so next thing we want to look at are properties of continuous functions. So it turns out that the continuous functions have some nice closure properties, in the sense that if you take two continuous functions and you add them, you get another continuous function. If you multiply two continuous functions, you get another continuous function. If you take a scalar multiple of continuous function, you get a continuous function. So these are a lot of nice properties, and they're actually pretty easy to prove. So I'll prove 1 and 4. And they all, again, they follow from the limit laws. So let me pull up OneNote, and I'll just do this work on the side. So what we have is the following claim. If f and g are continuous, at a, some number a, in their common domain. Yeah, I guess actually be a little more careful. All right, let's say we have two functions from function from d to real numbers, and g from the same set d to the real numbers. So they have the common domain, and they're continuous at a in the domain. Then f plus g and f times g are continuous at that same point. So here's the proof. Not hard. So let's do the f plus g case first. So we want to show, so what we want to do is we want to show that when you take the limit, I mean, it's almost trivial. Well, okay, let me back up a little bit. So by assumption, let me back up a little bit. So by assumption, we are by what it means to be continuous. We know that these two equations hold. That's just the definition of continuity. All right, so now let's take the limit as x goes to a of f plus g at x. Well, by definition of this, of f function addition, this is going to be f of x plus g of x. And now we know that these two limits exist, and in fact they equal f of a and f of g of a respectively. We can actually distribute the limit operator over the sum like so. G of x. And then by assumption, we know that this is f of a and this is g of a. So this is f of a plus g of a. And by definition of function addition, this is going to be f of g evaluated at a. And I'm actually not even going to go through the multiplication case. It's very similar. I mean, you can literally just take this addition symbol and replace it by a dot for multiplication. And then this one gets replaced by a dot, this gets replaced by a dot, this one does, and this one does too. So it's literally same calculation. And that's another powerful thing in mathematics is like arguing by analogy or arguing by symmetry. So these arguments are going to be the same, so you can just you don't even have to state the argument. So that's another general trick or technique you can use. All right, so now let's see. So we have all these rules. So we have that if you take a sum of two functions, there is going to be continuous. A difference is continuous. A scalar multiple, because C is a constant. A multiple multiplying two continuous functions is continuous, and the quotient of two continuous functions is continuous, provided that g of a is non-zero. So here's just a theorem. Actually, we proved this already, but they're proving it a little bit differently. This is kind of unnecessary, this proof here. So unnecessary. This is unnecessary because follows continuity of polynomials and rational functions follows from direct substitution property. So this proof is kind of unnecessary. It's another proof, and honestly, you could do this. You could prove the direct substitution property this way as well. If you want to look at that, you can pause. But it's unnecessary. So here's a nice theorem, and it's what you expect because polynomials and rational functions are the paradigm of a continuous function. This just says that polynomials and rational functions are continuous functions, which is, as I said, to be expected. So I'll just skip that. And so now that's going to be very helpful because to calculate limits like this, we just need to check whether or not function is defined at the limiting value and is it continuous. As in this example, we have this, we're taking the limit of this function f of x right here, given by this quotient. The domain is going to be this, it's just going to be wherever the denominator is non-zero. So you just set the denominator equal to 0, and you can see that x is 5/3. That will give you a 0 denominator. So you want to remove that point from the domain. It's not going to be part of the domain. But in particular, -2 is a point where in the domain is a point where the function is defined. So to evaluate this limit right here, this one right here, you could just plug -2 into the function. Actually, we saw this example. This is an example we calculated already. 1/-11. All right, so let's see. Here's some other limits. Not sure what this is about right here. See what else we have. There's quite a bit more. Oh, there's the intermediate value theorem. Let me see. I guess I skipped over this when I was first reading through the book. What is this about here? It turns out the most familiar functions are continuous at every number in their domain. Appearance of the graphs, the sine and cosine function. Yeah. Okay, so I mentioned this already. Sine and cosine functions are continuous, and that's a reasonable guess, and it turns out they are. So what is it saying here? Not really saying a whole lot, honestly. Let's see. So yeah, okay. Anyways, this is like I don't see this really being very useful. Um, the whole point of this discussion, it's not even that great, is that sine and cosine are continuous, and then so well tangent because it's a ratio of two continuous functions, right? That's by this theorem 4 right here. We're using this result right here. So because sine and cosine are continuous, the ratio, which is the tangent function, is continuous wherever cosine is non-zero, of course. So let's go back here. So this is continuous, except where cosine of x is 0, and this happens when x is an odd integer multiple of pi over 2. So you have these points of discontinuity and an infinite number of discontinuities. These end up just being the asymptotes, right? This is a point of discontinuity, point of discontinuity. These are infinite discontinuities. They're not removable. I think we kind of like argued for these limits in a previous lecture. So if you're not sure why the function goes off to infinity in this way, I refer you back to that lecture, which I don't remember which one it is. Um, Now here, all right, the inverse function of any continuous function is also continuous. Any continuous function. What? That doesn't sound right to me. I don't think that's right. Maybe for real numbers, I guess. That doesn't seem right to me, honestly. Continuous function whose inverse is discontinuous. Let's see. I don't think that's right. So they're saying I'd like the example function which is continuous at a point C such that it's invertible, it's continuous. Oh, but it's discontinuous there. Okay. But anyways, what this shows is that you have there. So this guy down here constructs a function. It's kind of horrible looking, and apparently it is injective, so it has an inverse, and it is continuous, but the inverse is not continuous. Yeah. So this it says that the f inverse is not continuous at 0. So I don't know why this book made this statement that if you take the inverse of any continuous one-to-one function, it's also continuous. That's not true. Uh, I can't say I didn't check all the details. I mean, you got this guy's got 15,000 reputation. He's got 12 upvotes on this answer. So I'm just gonna accept that I didn't check the details. I just searched for this. Now this is I'm guessing of the valid example of a function which is invertible or is injective, has an inverse, is continuous at a point, but it's not continuous. But the inverse is a discontinuous at a point, specifically f of c. Um, yeah, so this is yeah, I don't know why the book states that. This is false right here. But it's actually not, as you can see, it's not easy to prove that that's false. I mean, this is, as I said, this is a really complicated, it's a fairly complicated example. Um, so it's a function from the positive numbers to the positive numbers, and it's n over 2 of x is n, and it is an even integer, and then it's 1 over n plus 2 if x is an odd integer. It's 1 over 2n 2 times n minus 1 if x is of the form 1 over n, and then it just equals x in any other case. That's kind of surprising that this is continuous. Oh, and then I see. So this is not the function. All right, this g is probably not continuous, but they're going to define f. This is probably going to be continuous as also this piecewise function. Wow, I'm surprised that there's not a simpler example of a function which is continuous but whose inverse is not continuous. All right. Anyways, if you search for this, if you just example of a function that is continuous at C whose inverse is discontinuous. You can read through these details if you're interested. Maybe I will, because this is kind of interesting actually. Wow, this is a really weird example. Here's another guy. This is another example. This is a nice example. That's interesting. Take this bijection. Bijection from interval -2 to 2 to this interval, such as continuous and infinite. Oh, so they're saying here is a bijection. You define f on the interval -1 to 1 by letting me 0 at 0, and then it's of this form for, oh wow, that's really complicated. Anyways, you can see that there's multiple examples, but they're pretty non-trivial. That's surprising. So the whole point of this though is that this statement is false. The inverse of any continuous function is also continuous. This is not true. I don't know why they made that statement. But it turns out in this case, when you take the inverse of the trig function, when you look at the inverse trig functions, they are continuous. So when you take the inverse of a continuous function, it could be continuous, it might not be. It's not guaranteed. In this case, it is though. Now for this, we have so we have this exponential function. This is also going to be continuous, and so and also the inverse function in this case is continuous. Not always the case, but in this case it is. So here's a summary of continuous functions. You have polynomials, rational functions. These are the ones that are obviously continuous. Root functions are also obviously one continuous. Trig functions, inverse trig, exponential, and logs. Those are not obviously continuous. That actually is not terribly easy to prove. I don't think we're going to prove that in this course. We're going to just kind of take for granted that these functions squared off right here are just continuous. And from there, though, we can prove a lot of other functions are continuous. So the question is this continuous? So first of all, we know that ln x tan inverse x and x squared over x squared minus 1 are continuous functions. So when you take the fraction, when you take the ratio of these two functions, it's going to be continuous wherever on every point in the domain. So what's the domain? That's really the question about where is the function continuous just amounts to figuring out what is the domain. So what's the domain of this? Well, we have quite a few restrictions actually. So first of all, ln of x, we have ln of x in the numerator, so that implies that x has to be positive, right? Now tan of x, as it says, is continuous on the whole real line, so there's no restriction there. But then you have the denominator, so you don't want points where you have division by 0, so you have to solve for that, and that will give you plus or minus 1. So the two restrictions we have are this ln function appearing in the numerator, which implies that you have to have that, and then we want x squared minus 1 to be non-zero, so that implies that x is not equal to plus or minus 1. And when you combine these two conditions, you get that x has to be bigger than 1, which corresponds to the interval 1 to infinity, like we have here. So, oh, I'm sorry, actually, not quite. So really what we need are the restriction that x is positive and x is not equal to 1. And when you combine those, the domain becomes the domain is 0 to 1 union 1 to infinity. So so the question about where is this function continuous just reduces down to what's the domain of this function. Because if you take a ratio of two continuous functions, if you take a quotient of two continuous functions, and we are in this case, then the ratio, the quotient is continuous wherever it's defined. So the question about where is this continuous just reduces to a question about the domain. And I guess it's the same thing about this as well. This one's actually a trick question. So first of all, we have this ratio of these we have sine x, this is continuous, and then we have 2 plus cosine x, that's always continuous. So the function is going to be continuous wherever this is defined. So the biggest trouble we could have is where is um where this is this possible? So sine of x could be any number. You can plug in any number for sine of x. There's no restriction there. But the question becomes, is this possible right here? Or this is equivalent to cosine of x is equal to -2. Answer is this possible? No. Because we know that cosine and even sine is bound between 1 and -1. So there's just no x. So there does not exist an x such that cosine of x is equal to -2. So actually in this case, there's no problem. This number in the denominator is always going to be positive. To see that, you just take this inequality right here and you add 2 to both sides. So you get when you add, or sorry, when you add 2 to this inequality, you get 1 2 plus cosine x is less than or equal to 3. So it's bound between 1 and so 2 cosine x is bound between 1 and 3, so it's definitely never 0. So the point of though is that this thing is continuous everywhere because it's defined everywhere. It's defined on the whole interval. And in particular, that means we can compute this limit. So yeah, because it's continuous everywhere, it's continuous at in particular pi. So we can just evaluate this limit, not by using epsilons and deltas, but just evaluating the function at it. So we just plug in pi into this rational expression. So you get sine of pi plus cosine, so you get sine of pi right here, and then you get 2 plus cosine of pi, and then you get 0 over 2 minus 1, which is just 0. So I guess I didn't realize that we were evaluating the limit. I thought we were determining where is this thing continuous. But that's fine. We determined where it's continuous, and that allowed us to compute this limit. In fact, we can take the limit as x approaches any number of this quotient because we know that this thing is continuous. It's defined everywhere. It's continuous everywhere. So we can compute the limit in this way for any number, not just pi, not just pi here. We can do anything. So that's that example. So now we know that when you add continuous functions, you get a continuous function. When you multiply continuous functions, you get a continuous function. And so you might wonder, what about composition? That was another way of combining functions, right? We could add functions, multiply functions, divide functions, subtract functions. And if the functions are continuous, then um, any one of those combinations will be continuous. But what about compositions? Turns out, yes. So we have this first theorem right here. It says that if f is continuous at b, so you have a function f and then you have a function g, and if you're told that f is continuous at b, and you know that the limit of g of x as x goes to a is b, then when you want to compute the limit of this composition, so this right here is the same thing as f composed g at x. If you want to compute the limit of this composition, you could just plug in b. And I guess I prefer this way of wording it though. When you word it kind of just avoids having to state this number b. In other words, if f is continuous at this number at limit as x goes to a of g of x, then you get this equation right here. And what this says is that limits and continuous functions commute. These two operations commute. Taking a limit and then applying a continuous function, limits and continuous functions they commute. So that's what this theorem basically states right here. So in other words, like if f is continuous and if f is continuous at this number here, this limit right here, then when you want to take the limit of f composed with g at x, you can just bring the limit operation in. And that's going to be really helpful. So here's an example right here. So we have that, yeah, so arcsine or sine inverse is continuous function everywhere. It's a continuous function from, what is it, sine, arcsine. Arcsine inverse is a function from -1 to 1 to, I guess, negative pi over 2, I think, if I remember correctly. So this is continuous, and we know so that, and then also this function is continuous also, this function on the inside of this composition. So if we want to compute this limit, we can actually just bring the limit right inside of the composition, this arcsine. And what we do have to do here is we can't actually we can't just do this limit right here by direct substitution, because if you plug in 1 you get 0 over 0. But what you can do, and they did this, let's see, what did they do here actually? Oh, okay, all right, yeah, that's kind of being sneaky there. So what they did is they factored the denominator here, so into here. So watch, if you FOIL this denominator right here, you get 1 minus square root of x times 1 plus square root of x. You FOIL that, you get 1, and then you get plus square root of x, and then minus square root of x, and then minus square root of x squared. You cancel these terms out, you get 1 minus square root of x squared is just x. So that's kind of tricky. I didn't notice that at first, actually. So what the way to avoid this 0 over 0 problem when you plug in 1 is to factor the 1 minus x in this way here. And this is a verification that this is a correct factorization. And then the numerator here cancels with this term right here. And then all you're left with is the 1 plus square root of x. So you have 1 over 1 plus square root of x. And then you just plug in, now we can use the substitution property. We can just plug in 1 to get 1/2. So we have arcsine of 1/2. And I guess if you consult your unit circle, that's how you get pi over 6. So that's an example using this theorem here, theorem 8 right here. So you can just, again, this limit right here commutes with arcsine because it's continuous. It's a continuous function on its whole domain. So you can just draw the limit in here like that, and then do this kind of crazy trick right here. I guess that wasn't obvious even to me. All right, so this is just that's not really that important. So what you get from theorem 8 is theorem 9. It's just a more general statement, I guess. Yeah, so they're gonna actually prove this theorem right here, and they apply theorem 8 right here. If you want to read through that, you can. I'm not gonna go. Well, I guess I will. What does it say? I'll go through the proof. It's not that long. So G is continuous at A, and then you told that F is continuous at G of A. Then the composition F compose G is continuous at A also. So in other words, what this says is that composition of continuous functions is continuous. Another way of saying that is that continuous functions are closed under composition. If you compose two continuous functions, you're going to get a continuous function back. So what this says, what's the proof? So G is continuous at A. So this is by definition of what continuity means, right? That this limit condition holds. Now, since F is continuous at G of A, which you call B, you can just apply theorem 8, right? So you can, when you take this limit right here, you can draw the limit in. I don't like it, but that's actually kind of. Let me see if I can add a step in, because I don't like the way they did that. So limit of f of g of x. So now f is continuous at g of a, but what is g of a? It's the limit as x goes to a, right? Of g of x. So what you can do is you can bring this limit in according to theorem 8. I don't like the way they're doing the proof. And now that you've drawn this limit in, now you can take the limit of, you can compute this limit because you know by definition that it is g of a, because g is assumed to be continuous. So this is going to be uh, g of a. So that's exactly, this is exactly the statement that f composed g of x is continuous at a. All right, let's see. So almost done. I think we just got this intermediate value theorem problem. Yeah, okay. I guess they have these two examples. So are these functions continuous? So you have x squared is continuous and sine is continuous. So yeah, when you compose the two, it's going to be continuous. So yeah, so there, not much to do there. Now, but was this one continuous? This one you got to be careful because there are cases where cosine 1 plus cosine of x can be 0, right? And you remember ln of x is not defined at 0. So you got to, it's going to be continuous whenever that is not 0. So, but no, so first of all, the domain, the numbers that you're allowed to plug in to ln, the natural log, have to be positive. But we know that this thing is always positive, right? Um, or non-negative, I should say, because we have this inequality. This is the inequality I stated above. So if you add one to both sides, you're going to get this. It's cosine x less than or equal to 2. But you have less than or equal to. So it's possible that you could have a actual equality. So the good news is though is that this is if you're not 0, then you're going to be automatically positive, right? So it will be defined when this is positive. So you just need to figure out when is this equation true, which is the same thing as cosine of x is equal to -1. So it's going to be undefined when cosine of x is equal to -1. And if it's not defined for such x, then it definitely can't be continuous. But just consulting your unit circle, you know that cosine of x is equal to -1 when x is some odd multiple of pi, plus or minus pi, plus or minus -3 pi, plus or minus 5 pi, etc. So it's going to be defined whenever x is not of this form right here. And if it's defined when x is not of that form, then it's continuous because it's composition of otherwise continuous functions. And I guess this is a plot right here. So you got like asymptotes at those points. This would be like, I guess, pi, this would be negative pi, this would be 3 pi, this would be -3 pi, etc. All right, so the last thing we want to look at is the intermediate value theorem. And this is we're not going to prove this, is actually kind of tricky to prove, but this is actually a pretty intuitive idea, even though the proof is tricky. It's an intuitive idea, and that's a sort of annoying thing in mathematics. Like you have these statements that, like, yeah, they make sense. Like, yeah, this morally speaking, if the universe is fair, um, then the statement should be true. But sometimes the proof is not so obvious, even though the statement is obvious. So what the intermediate value theorem basically states is that when it's a statement about continuous functions, and basically what it says is that if you have a function and you know and you know that, I don't want to say this, if you have a function, continuous function, and you know that has a lower bound and an upper bound, then it actually has to take every number between those bounds. And this idea is kind of like encapsulated, I guess, in the idea that if you look at like rate of change of position or velocity, say velocity, if you you're going 50 miles per hour, so that's a lower bound, and then you travel to 60 miles per hour, you increase your velocity to 60 miles per hour, that's your upper bound, then you have to pass through every velocity in between, right? And I mentioned that at the beginning. So how do you state that mathematically? Well, here's how you do that. So you start with f as a continuous function on the closed interval um, a to b. So f is a function from the interval a to comma b to the real numbers. And then n is any number between f of a and f of b. So like think of f as velocity, instantaneous velocity, if you want. Of course, you do need these to be not the same, so you're not talking about the same velocity, for example. So now, if you have a continuous function and you have on this closed interval and you have a number n between f of a and f of b, then there actually has to exist a number c such that f of c equals n. That is that number n is the output of the function at some point. And so what that means is like, again, going back to the example of velocity, if you're going 50 miles per hour at some point and then you go 60 miles per hour at another point, there had to have been some point between. You don't know what point. It just says that there exists this number, exists this time where you were going, say, 55 miles. You don't know what the time was, maybe. You don't know exactly what, you weren't clocking it, say, you weren't measuring the time, but you know you had to have gone 55 miles per hour at some point in time. And this is kind of a weird theorem because it just says that this number exists. It doesn't tell you how to find the number. It doesn't tell you, there's no way of calculating the number. It just says it exists. And you might be wondering to yourself, like, how is that useful then? But it turns out, even though you don't know what this number is or how to calculate it or compute it or construct it, it's this theorem ends up still being extremely powerful and useful in proving other theorems. So here's a graphical representation of what's going on here. So you have this blue curve. It's the graph of f, which is some continuous function, and then you have f of a here, and then f of b, and then you have some number n between f of a and f of b, and you can see, well, if the function is continuous, and you look at this line through n, yeah, it's got to intersect somewhere, and so there's some corresponding c value. There might be a lot, as B shows, there could be a lot of numbers actually. In this case, there are three different points. But all the theorem says is that there exists one. There might exist many others, but all we need is at least one. So what is let's look at an example. So here's an interesting example of how to use this theorem. So you have this equation, and maybe it doesn't factor easily or you can't solve for it easily, but you just want to show that there is a solution to this equation between 0 and 1. Well, here's how you do this. So you're going to define f to be this polynomial right here in this equation. And then what is this, we want to rephrase this question differently. So looking for a solution to this equation is equivalent to between 1 and c is equivalent to finding a number c between 1 and 2 such that f of c is 0. So this is an equivalent way of understanding this problem or this question. So the question is, can you find a solution to this equation that's between 1 and 0? And that's equivalent to asking, does there exist a number c between 1 and 2 such that f of c is 0? So this should definitely just immediately remind you of the intermediate value theorem. That is we want to use that. So kind of referencing the intermediate value theorem up here, you have this interval a to b. So we're gonna say a is equal to 1, b is equal to 2. So f is going to be defined on the interval 1 to 2, and it goes to the real numbers. And in our case, capital N is 0. We want 0 to be the output of a function at some point C. Well, how do we do this then? Well, we need to show that when we evaluate f at 1 and then f at 2, that 0 is between them, and we get that. So if you evaluate f at 1, you plug 1 into this function here, you get 4 minus 6 plus 3 minus 2 is -1, and that's definitely less than 0. And if you plug 2 into this function right here, you get 32 minus 24 plus 6 minus 2 is 12, and that's definitely bigger than 12. So in other words, you have f of 1 is between sorry, 0 is between f of 1 and f of 2. So by the intermediate value theorem, so we have n is between them. So by the intermediate value theorem, there has to be a number c. So there has to be, so the intermediate value theorem says that there's a number c between 1 and 2 such that f of c is 0, which we know is equivalent to saying that this equation has at least one solution in this interval right here. And so actually, even though that we don't know what this number c is, all we know is that it's between 1 and 2. We can actually keep using the intermediate value theorem, keep applying it again and again to kind of like narrow in on what c might be. We're not going to get we probably won't get an exact number for c, but we'll get a better estimate. And the way you do that is you shrink the interval, or you like consider a different interval. So what we're gonna do is, let's see, what are they doing here? I guess what they do is they're gonna say, look what they do. So now they're gonna consider f on the interval from 1.2 to 1.3, and then evaluate to r, of course. And f is this same polynomial right here, which comes from this equation. And what they see is that f of 1.2 is less than 0, and then f of 1.3 is greater than 0. So 0 is between f of 1.2, f of 1.3, so there has to exist a number c. So now c went from being between 1 and 2 to now being between 1.2 and 1.3. So that's a really smaller interval. I should point out that this number c that you get from considering this interval could be different from the number that you get from considering this interval right here. Like up in this case right here, right? We had multiple values of c equaling who's f of we had c1, c2, and c3 such that f of c1, f of c2, and f of c3 all equal n. So that's entirely possible that when you do this refined calculation on this smaller interval, you get a different number c. And then they do a refine an even better refinement, and they find that when you get the function at 1.22 is less than 0, and the function evaluated at 1.23 is greater than 0. So 0 is between these. So again, there's going to exist a number on this interval, possibly different from the one you considered on this interval from 1.2 to 1.3, and possibly different from the one that you got, the value of c that you got from the interval 1 to 2. All right, so that's all we're going to do. That's all we have for this video. Let me stop sharing and end this.